So hello everyone. So welcome to our this week Rutgers Efficient AI seminar. Today, we're glad to have the Professor Yuhao from the University of Rochester to give us this talk on the very interesting topic, visual computing. Professor Zhu is currently assistant professor of the computer science department at the University of Rochester. And I believe Yuhao, you graduated from the UT Austin, right?
Yeah, that's right.
Yeah, and you once had the industrial experience in the ARM research, I remember. And Professor Zhu's group focused on the applications, algorithm, and systems for the visual computing. His work is recognized by the honorable mention of the 2018 ACM ThinkArc IEEE CSTCCA Outstanding Dissertation Award, multiple IEEE micro topics, designations, and the multiple best paper awards nominations in the computer architecture, virtual reality, and the visualization. So more about his research, you can find that from his research group website. And now let's welcome Professor Zhu to give this talk.
Yeah, okay, all right. Thanks for the introduction and thanks for inviting me. So I'd like to talk about visual computing today. So you all can see my slides, right?
Yes.
Okay, all right. So I'd like to start my talk by introducing you to my first ever phone, which is this Nokia 3310. And this is arguably the second most successful phone ever, second next to iPhone 1. And I don't know how many of you have used the phone before, but I certainly have spent a lot of time playing with this Snake game. It's one of those classics. And that was how to play Snake back in 2000. But this is how we play Snake today, right? Even on a smartphone, on a cell phone, we can, have realistic 3D rendering, physics engines, even stereo acoustics. We can use the phone as a joystick to interact with the game. The point is that mobile devices have become more capable, much more capable over the years. Every generation, mobile system designers are able to push more performance into these devices. But the flip side is that the energy consumption has also been increasing. So if you only had to charge your phone every 3 days back in 2000, well, you probably have to charge your phone 3 times a day. So that's just indication of the increase of energy consumption. So the problem with this is that the battery density is not improving. And so the only way of improving the total energy capacity is to increase the form factor, is to increase the size. So this is a plot, a study we did when I was back in grad school. So we mined 600 top-selling smartphones on the market, and the figure plots the battery capacity on the y-axis and the screen size on the x-axis. We couldn't really get the battery size, so we used the screen size as sort of a proxy. And as you can see, there is sort of a linear relationship, and that shows you that to increase battery capacity, you have to increase the size, the form factor of a mobile device. And that's why we've gone from smartphones to phablets to tablets, and things are getting bigger and bigger. And so maybe in the near future we're going to be holding these giant devices 2 hours just to be able to talk to our friends. So I mean, I don't know about you, but I'm sort of rejecting that future. I think that the future is going the other way, where devices have to become much smaller. If you think of this augmented reality device, right? So it's so much smaller than your smartphone. So if we're concerned about the energy consumption of our smartphones, well, think of how small of a battery that can be accommodated in this very small AR device. But the problem is that at the same time, these AR devices are supposed to be doing much more work than your smartphones. They are supposed to be always on, constantly sensing the environment, running computer vision algorithms, AI inferences maybe, and so to provide immersive user experience and intelligent services to us. I mean, it's doing much more work, but with a much limited energy capacity. And so even though I'm talking about AI, but I think AR, but I think AR is representative of a range of emerging application domains like drones, self-driving cars, VR, things like that. So I call these visual computing applications. Now, if you look at these application domains, they share common characteristics in the sense that they have to simultaneously acquire massive visual data spatially and temporally. they have to interpret visual data to provide intelligent services. And optionally, I mean, in the case of AR and VR, they have to generate visual data for immersive consumption. So these are the common traits of the application domain, the visual computing application domains that I'll be primarily focused on today. To just show you sort of what I really mean by acquisition, interpretation, generation, if you look at this AR device, so this is sort of an AR glass that you can wear, and it's going to draw the virtual chessboard and lay this on top of the table, which is in the physical world. So this is the end-to-end pipeline, the true end-to-end pipeline where lights from the scene come in and lights from the display enter your eyes. Lights in, lights out, right? That's the truly, end-to-end pipeline. And you'll see that it relies on, the camera, including the optics and sensors to acquire images. And then you run some, computer vision algorithms on the processor that interpret the images to, in this case, estimate the pose, the orientation of the table, so that GPUs can render the virtual chessboard and properly overlay this on top of the table, right? And then the overlaid chessboard is going to be displayed to you, so lights enter your eyes, right? So in this sort of grossly simplified pipeline, it exercises simultaneously acquisition, interpretation, generation at the same time. Now you might be wondering what's interesting about this. I mean, we all remember, on the left is the wild Pokemon Go game. I mean, we all remember that was an internet sensation, and it was a real AR application running on commodity smartphones without requiring any extra hardware. So, from what we know how to build to what we sort of envision in the future on the right, is it going to be a natural evolution of technologies, or it's going to take some sort of revolution? And in this talk, I'm going to make a case for revolution. And to understand that, we have to look at how sort of today's research is, right? So what are we doing today? So I would argue that in this community, in sort of architecture and systems community, we have been primarily focused on interpretation, on optimizing the processors. And we've been taking sort of this vertically integrated cross-layer approach. We do this software hardware co-design from programming models to compilers and runtimes and hardware accelerators, even low-level devices and so on. So it's a vertically integrated approach, and it's incredibly important. It's here to stay, right? It's not going anywhere. And so these are just some of the concrete examples. But if you really look at this end-to-end pipeline interpretation stage, or optimizing the processor is just one stage of the end-to-end pipeline. And what we have been doing is to optimize the interpretation, optimize the processors to the extremes. We improve its performance, lower its energy, and so on. And this mindset, actually, if you talk to camera people and display people, it's very similar to what they are doing. They optimize for their own sort of subsystem. So sensor people aim for higher signal-to-noise ratio, higher dynamic range. Optics people try to widen the field of view, reduce aberration, optical aberration, and display people try to accommodate more colors, widen the color gamut, and improve the color reproduction accuracy and so on. So I would say that every what we have been doing in this sort of what we have been doing is to sort of design and optimize subsystems, and then we simply slap and stitch together these individually optimized subsystems and call it a day and say that that's the system. But as you can see, this is more or less optimizing for local optimum, right? It's not really optimizing for the end-to-end system, for the user experience. So what I'm advocating for is this horizontal pipeline, where we take a step back and look at the actual application, the end-to-end application, where lights in, lights out. How do you optimize the whole system? And I would argue that the strategy, the spirit, is very similar to the vertical approach, where we blur the boundaries across layers vertically. It's the same thing. We have to blur the boundaries, but this time horizontally across different domains. Okay. Another way to say this is that now we have to rethink the interfaces or abstractions across these domains, across these subsystems. And this talk is going to be sort of a whirlwind of some of the most promising and I think exciting directions in this horizontal paradigm. And I'll talk about some of our recent work in the horizontal paradigm here, okay? So I don't know how the format is, but I would be happy to entertain questions in the middle of the talk. But if if you have any questions, you feel free to just speak up or just use the raise hand feature on Zoom as well. Okay. So the first thing I'd like to talk about today in the horizontal paradigm is what I call computational image sensing, which is essentially pushing computations inside image sensors. So if you look at the pipeline, right, so any visual applications, whether it's AR, VR, self-driving cars or robots, it relies on vision informations. So where are the visual information from? Well, they are from cameras. And typically the image sensors capture pixels, raw pixels, which are then transmitted through the what's called MIPI CSI interface to the processor, to the chip. Now, as you know, transmitting data consumes much more energy than computation. So this is data from Meta, normalizing to 1 byte of MAC multiply accumulation operation, transmitting 1 byte through the MIPI CSI interface from the sensor, from the camera sensor to the chip, consumes 2 orders of magnitude higher energy. If your image sensor has, if your sensor node has no compute capability, you probably have to transmit the data back to the cloud. Transmitting 1 byte of data through Wi-Fi consumes even higher, 5 orders of magnitude higher energy than doing computation. All this is to say that we ideally want to reduce the computation, transmit as few pixels, as little data from the sensor as possible. Well, so the very natural idea is to then move computations inside the sensor, right? So for instance, in the extreme case, let's say in the downstream algorithms, I'm running object detection algorithm. And if I can completely run the object detection algorithm inside the sensor, all I have to transmit outside the sensor is just the object label and maybe the location, the ROI location, right? That's sort of the extreme case, but the idea is to move computation to the sensor. And this is by no means a new idea by today's standard. But this is sort of an illustration where on the left is today's paradigm, where you have the image sensor that is responsible for capturing pixels, which are then transmitted to the host, which could be a local sort of edge device or could be the cloud. What we're moving towards is what's on the right, where you have sort of die-stacked image sensors where you have multiple layers. So this is one form of die-stacked image sensors where you have 1 pixel layer, pixel array layer that's responsible for capturing photos, capturing pixels, transforming photons to electrons and pixels, and that's what camera sensors are supposed to do conventionally. You can also have a DRAM layer to buffer data, and then you can push some of the computations into the sensor by having a computation layer on which, for instance, you can have some simple image signal processing and even neural network accelerators. So these are not even recent image sensors, but the one on the left is from Samsung, in which we can see that they have 2 layers. And they have a simple image signal processor on the second layer. And the one on the right is from Sony. It's got 3 layers, and there is an ISP, the image signal processor there as well. This is slightly recent, I think. So this is a stacked sensor where they have the pixel array, the DRAM layer, and the logic process substrate, which is basically for computation. And I think Sony recently came up with a die-stacked image sensor where they literally integrated a neural network processor inside the sensor. So all this is to say that you can more or less treat a sensor as a full-fledged processor that can do non-trivial computations, and that is the premise for us to move or push computations inside the sensor. Okay, now you might think that this is simple. We just push, take, let's say, a neural network that's supposed to be running on SoC and just move into the sensor. Problem solved. Well, it's not quite that simple. There are at least 2 limitations or sources of inefficiency of doing computations inside the sensor. One is that the image sensor is typically much smaller compared to a processor, right? So the area is typically at least 1 order of magnitude smaller, which means the peak throughput you can get from the sensor, the computation throughput you can get from the sensor is much lower. And secondly, more sort of for a practical reason, because sensors are typically much cheaper, right? Like 1 order of magnitude cheaper. So you can buy a decent sensor for $10, which is nowhere close to the cost of sort of a high-end chip. Because of cost considerations, the fabrication, the process node of a typical image sensors is usually 1 or 2 generations behind the process node used for manufacturing processors. And because of that, computations inside the sensor would also consume more energy. So for these 2 reasons, computations inside the sensor are inefficient. So then it sort of naturally leads to the question of what exactly do we compute in sensors, right? So we ideally want to move computations inside the sensor so that we reduce the data transmission out of the sensor, but at the same time, we cannot do too much computation because it's inefficient to do that in sensor. So the ideal sort of algorithm pattern that can benefit from computing in sensor is what I drew here. So this is a bit of sort of a cartoonish illustration. On the front left to right is sort of how the application or the algorithm executes over time. And the width here is sort of indicates the input data volume, how much data you have that goes into your algorithm. And here is how much data that you're supposed to get when the algorithm finishes. Okay, so the ideal algorithm pattern that fits in sensor computing is where it can use trivial amount of computation, spend very short amount of time, trivial amount of computation that can dramatically reduce the amount of data that you have to transfer outside the sensor. And that trivial amount of computation is ideally what you want to compute inside the sensor, right? It allows you to do just a little bit of computation so that the inefficiency is not going to matter too much, but that allows you to reduce the data volume by, let's say, orders of magnitude, so that you can reduce the data transmission overhead. A desirable side effect of this pattern is that since you shrink the data volume early on, the overall computation reduces as well, right? So this is sort of the ideal algorithm pattern that can benefit from in-sensor computing. Unfortunately, this is not what today's algorithms are built for. If you look at sort of canonical convention neural networks or convolutional neural networks, the data volume typically increases in the beginning because you use lots of filters to extract features. So conventional CNNs, the data volume would grow initially and then only shrink at the end, right? That's not the pattern that we're looking for. If you look at computational photography pipelines, what they do is it's sort of a linear pipeline where every stage takes an image in, produces another image. So the data volume stays roughly constant throughout the pipeline. Again, not the pattern that we're looking for. If you look at autoencoder, encoder, decoder architectures, the data volume does shrink in the encoder layers, but the data volume shrinks too slow or too late. It takes non-trivial amount of computations to shrink the data, right? So that's too late. And if you were to push this into the sensor, you would have to push all the encoder layers into the sensor. That would be inefficient as well. So the moral of the story here is that we can just take one of existing algorithms and push it into the sensor. What we have to do is to design algorithms for in-sensor computing. In other words, we have to build algorithms that by construction have this ideal pattern that can benefit from in-sensor computing. And I'm going to talk about, real quick at the high level, 2 promising ideas or 2 promising directions along this line. One is what I call event-driven in-sensor ROI. ROI stands for region of interest. And then the other is what I call incremental computation using sensor metadata here. Okay, so I'll start from with the first idea here, which is event-driven in-sensor ROI. And I'm going to use eye tracking, which is widely used in AR/VR applications, but other application domains as well, as sort of the case study as a running example here. And so at the very high level, what an eye tracking pipeline needs to do is to take a sequence of near eye images on the left captured by a near eye camera and figure out the gaze, which is where your eyes are looking at every single frame, which is illustrated on the right. And typically you run a gaze tracking neural network. Typically gaze tracking is done by neural networks, and they are incredibly accurate, but also very, very slow. Okay. So our idea here is that given a near eye image, right, only the region of interest contributes to the gaze information. The background, as far as the eye image is concerned, the sclera, the eyelids, the eyelash, and all those things are not really contributing to the gaze information. And so what we need to do is to extract the ROI information and only transmit the ROI to the processor on which you run the gaze tracking neural net. Now you can certainly run an ROI detection algorithm or even a neural net inside the sensor, but that would defeat the purpose because you're running some computationally heavy algorithm. So our idea is to use the notion of events. What I mean by events is essentially a per pixel activation map. So for each pixel, we look at how much it has changed between two consecutive frames. And a pixel is only activated if the luminance, if the pixel intensity has changed above a particular threshold, and then we would activate the pixel. And so by comparing two consecutive frames, we're able to get what we call the event map or the activation map, which is what we show here. Now, if you look at the event map, you can sort of see that the ROI information is naturally encoded there, right? So, you know, the part of the eye that's relevant for gaze is already there. And so essentially the event map is a sort of handcrafted feature that encodes the ROI information from which we can then very easily extract ROI. So what we did is to get or extract the event map and then feed the event map into a tiny little 5-layer neural network. So it might look complicated in terms of the network architecture, but it's just a very simple network. In terms of the MAC operation, it's several orders of magnitude lower compared to the heavy gaze tracking neural net that you would run. So it's just a tiny neural net that you can push into the sensor. So the event map goes into the neural net, which produces or predicts the ROI, and the ROI is what gets transmitted to the processor, to the SoC on which you run gaze tracking neural net. And so everything up until this point, or run inside the image sensor. Okay, and so because of this, we're able to get 5 times speed up with no perceptible error loss, accuracy loss. And we can achieve about 15% energy reduction. The end-to-end pipeline, the end-to-end system can enjoy 15% energy reduction. Okay, so that is about the sort of first idea of in-sensor computing, which is to use events to extract ROI, which allows us to reduce the data transmission overhead. The second idea I'll talk about is what I call incremental visual computing, and the way to think about this is that if you can regard each vision algorithm, whether it's neural net or classic vision algorithm, as just a function f, and typically it takes a sequence of inputs, right, a sequence of frames, let's say over time, and it produces a sequence of frames over time. It produces a sequence of outputs over time as well. So xt plus 1 produces yt plus 1, and so on. So, you know, mathematically, that's how computation is carried out. So you can basically, for every frame, you run this, execute this function f. Now, this function f is typically very computationally intensive, right? So let's say you run object detection neural net, and that's computationally intensive, and that's ideally what we want to optimize. So our idea is to, you know, rewrite those equations in slightly different form. To compute yt plus 1, we can approximate it in this equation. Now, if you stare at this equation for long enough, you realize that it's nothing more than just a one-term expansion of Taylor series. And this one-term expansion of Taylor series is an accurate approximation of the original function f, if f is locally smooth. If you remember from your Calculus 101, that's one of the major conclusions there. And this vision algorithm f is typically locally smooth in the sense that if the inputs x is off just by 1 pixel, the output shouldn't dramatically change, right? So most of the vision algorithms we care about have this locally smooth property. And so that would allow us to use this expansion as approximation. Now, if you look at this approximation, sort of new way of calculating output, there are 3, you can think of it as composed of 3 operators. The first operator is what I call, is basically calculating the difference between 2 consecutive inputs, right? Now, once you've got the input difference, the second step is to convert the input difference to output. So delta input to delta output. That's sort of what the second operator is effectively doing here. Once you've got the delta output and you have the output, the previous output, all you have to do is to update the output using the delta output and the previous output to get the new output, right? So that's the way to look at these this approximation. It's really these 3 operators. Now, in practice, these 3 operators are hard or sometimes even impossible to calculate exactly because well, we don't have the analytical form of the function f to begin with. Well, then we can't really calculate, precisely derive the analytical forms of the three operators. So, but it's an approximation to begin with, and so what we typically do is to approximately calculate these three operators, or to represent these three operators in application specific way. Okay, so I'll show you a trivial, perhaps the most trivial example that leverages these approximation, and that's object tracking. So that's the formulation there to remind us what we're talking about here, the three operators. That's the equation there. And object tracking is the task of taking image and somehow assuming that you've already detected the object and you want to track the trajectory of the object. So now if you think of object tracking and using this formulation, the first step is to calculate delta input. And so delta input, in the case of object tracking, delta input can be seen, or you can use pixel motion as delta input. And pixel motion typically is represented as motion vectors, which is essentially the movement, the offset of every single pixel tile, which are sort of indicated by the arrows here. Now, the interesting thing is that the camera sensor, as part of denoising, inherently generates the motion vectors, the pixel motions for us. All we have to do is to retrieve it from the sensor, right? So that's part of the metadata I was talking about. You don't have to calculate that, it's already there. All you have to do is to get the motion vector data, and that's something that you can use as delta input here. Once you've got the delta input, the next step is to convert delta input to delta output. Okay, now what is delta output here? In this particular application, what we care about is the movement of the entire object, not individual pixels. But if we have individual pixel movements, all we have to do is to average it across the ROI of the object. That gets us the average motion of the object, and the average motion is naturally delta output. And the last step is to update the output. You have the location, the position of the previous location of the object. You have the movement of the object. All you have to do is to extrapolate, basically an addition, a vector addition that gets us the new location of the object, right? So that's what the three operators are doing. And as you can see, the second and third operator are almost zero overhead. The second thing is averaging across a few vectors. The third thing is literally just adding a vector, right? So the second and third operators are basically zero cost, free. The first operator is what's costly, but we don't have to do that. It's already there. It's given by the sensors. All we have to do is to retrieve it. So I'll just show you some headline results. If you run a heavy-duty object tracking neural network versus using our approach, which is to execute the whole thing inside the sensor, we can reduce the total number of MAC operations per frame by over 6 order of magnitude, right? That shows sort of the benefits or the efficiencies of this approach. Okay. Okay, so that sort of wraps up the first part of the talk, which is computational image sensing. And I'll then, what I'll talk about next is what I call perception guided sensing and rendering, which is about reducing the rendering and display power by exploiting the characteristics of human visual systems. And so I'm talking about this in the context of AR and VR. And one of the main sort of characteristics of AR and VR is that these devices provide a very wide field of view to enable immersive user experience. So if you hold your smartphone at arm's length, the entire display is within about 25-degree field of view. When you are wearing a VR headset, the field of view is about at least 160, right? Because it wants to provide an immersive experience as if you are in a new virtual world. So the field of view is typically higher. When the field of view is higher, you have to render more pixels, you have to do more processing. So there is a cost of, at the expense of more processing, they can provide a wider field of view. And so the goal here is to reduce the processing overhead without sacrificing sort of the immersive experience. And the observation here, though, is that even though these devices, AR/VR devices, provide a very wide field of view, literally lights are coming in across a very wide angle, your human visual system, the retina processing is heavily favoring the data on the center of the retina, which is what we call fovea. Now, the peripheral of the retina, which has higher eccentricities, your peripheral visual acuity is actually very low. Now, you can do a very simple experiment, actually. So if you just, fixate it straight ahead, and things in your peripheral vision, you can tell that there's stuff going on there, but you cannot really make out the details. The high frequency details in your peripheral vision is sort of lost, right? And the reason is because if you look at the figure on the left, the photoreceptor cell distribution, I mean, that's, you on the retina, you have millions of photoreceptors. I mean, that's what allows you to see things. The photoreceptor distribution, if you look at the red curve, is heavily concentrated on the fovea where the eccentricity is 0. As soon as you move away from the fovea, the photoreceptor distribution drops sharply. And that's a fundamental reason why your peripheral visual acuity is very low. You can't really see things, make out details in your peripheral vision. What this means is that even though you have to generate information across a wider field of view, only a small portion of it needs to be of high fidelity. The peripheral pixels, you don't really care as long as there's some stuff there, right? Your goal is to maintain, our goal, I should say, is to maintain the same user perception while reducing the processing overhead. And in particular, we're talking, in this work at least, we're talking about color perception. So basically, the idea is that you can't really tell with high accuracy what color is it in your peripheral vision. Yeah, your color vision is sort of confused in the peripheral. And so we recruited a bunch of human subjects or participants or users into the lab, and we performed psychophysical studies to sort of understand human color perception. And so this is sort of the experimental setup where the user is literally wearing a VR headset. And so this on the what's on the computer screen is what they actually see. So they are not really looking at the computer screen, but what's on the computer screen is what they actually see when wearing the VR headset. Now, what they are asked to do is to fixate or stare at the cross here. Okay, so they're asked to fixate, to focus only on the cross. What this means is that the 4 dots or the color patches are going to be in their peripheral vision. If you look at these 4 dots here, I mean, it's probably not super clear here, but these 4 dots, 4 colors, 4 dots actually have 2 colors. 3 of them, in this case, this one, this one, this one, they have the same color. This is a different color. It's randomized, so they don't know where the different color patch is. What they are asked to do is to identify the different color patch. In this case, if they could actually tell the difference between the 2 colors, they will tell us that this is a different color, the other 3 are the same. Okay, so, and we did, thousands of trials, and I'll show you a video as far as what they actually see while wearing the VR headset, what they actually see during the experiments. So there's no sound here, which is intentional, but just focus on the video. So you see that there are always 4 patches with one patch that has a different color than the other 3, and the different color patch is randomized, and the participants are asked to identify the different color from the other 3 patches. All right, I think that's probably it. Okay. Now, the data we get from the psychophysical studies is the following. So remember, so this is the sort of the retina, and fovea 0 is the eccentricity 0 is a fovea where your visual acuity is the highest. Okay, so I'm showing you data at eccentricity 10 at 10 degrees, so slightly away from the fovea, where your color perception is slightly worse than fovea. And what I'm showing you here is, so this is the 2D color space, or projecting a 3D color space into 2D. So we know that color space is 3D, but 3D is harder to visualize. We're just showing you sort of a 2D cross section, 2D slice. Okay, and you'll see these crosses. So if you look at this ellipsoid or ellipse, the cross is the reference color, and all the colors within the ellipse are perceptually the same as the reference. Similarly, the data here shows that all these colors in this ellipse are perceptually no different from the reference color here. Okay, so this is for one particular subject. We did this for, I think, 5 subjects, 5 users, and you'll see that and I'm showing you data for the other 2, for two another users. And you'll see that the data are not exactly the same, but they more or less follow a trend where the boundaries are ellipse-like. So this is the data in 10-degree eccentricity, where your visual acuity is slightly worse than fovea. Okay, now if you look at the data at 25-degree eccentricity, one thing you immediately see is that the ellipsoid sizes grow. That basically means that users will confuse more colors. Their color perception acuity becomes worse because more colors are perceptually similar, right? As we move away from the fovea. So this is the eccentricity at 25-degree. If you look at the eccentricity at 35, and these are the experimental data from the 3 users, and you'll see that the ellipses become even larger. So the aqua perception ellipses, the sizes become larger as eccentricity increases, which makes sense because as eccentricity increases, you are moving more to your peripheral vision, in which your color perception acuity is lower. You're more easily be confused by different colors there. Okay, so but that's just experimental data. We need to have a computational model for that allows us to sort of capture it. So the idea is to build a computational model, and the model would take the following parameters or inputs. The first input is sort of the reference color, the RGB values of the reference color that we want to match, and also the eccentricity, 10-degree, 25-degree, or 12. And then given these 2 inputs, we regressed a model. We actually use a very simple neural net to regress the model from over 8,000 user trials. And what this would provide us is the parameters of the ellipsoids that's associated with the reference color at a particular eccentricity, right? So to model an ellipsoid, you need 3 numbers, alpha, beta, gamma. And so given these 3 parameters, you can then construct an ellipsoid, an equal perception ellipsoid of the reference color, where all the colors inside the ellipsoid are perceptually the same as a reference color. Now, to visualize that in 3D, that's how it looks like. So we're visualizing the ellipsoids in the linear RGB color space, and you will see that all those ellipsoids. And so basically, colors in the same ellipsoid are perceptually the same. Okay, that's what we are able to sort of computationally model from the user studies. Now, you might be wondering, why are we talking about color? I mean, it sounds like it's cool to talk about color models, but like, why do we care about this from a systems point of view? Well, it turns out that the display power is dictated by colors. I should have a video for you, but I don't think I have that. But this is the color sort of display power measurement setup that we built. So this is a pair of display modules that's used in VR headsets. And you have a current sensor, and that's interfaced with Arduino board, which runs a driver that we wrote that collects the power data, and then the power data is then transmitted to the host, and we can plot the power. And so as we cycle through different colors, the power on the y-axis changes. So at least as far as emissive displays like OLED, which is almost everywhere, the power consumption is dictated by color. The reason is because for emissive displays, the color is dictated by the amount of light each subpixel emits. And so if you want to emit more lights, well, then you have to drive it, use higher current, which increases power consumption. So so we put the display under a microscope. And so these are microscopic photos of the display at different colors. And as you will see, if you display white, well, then all 3 subpixels, RGB subpixels, will emit sort of maximum light, maximum power that consumes higher power, right? So this is to show you that power consumption, display power consumption, is dictated by color. It turns out that there is a sort of a linear relationship, or we can fit or regress a linear model to estimate the power consumption from the R, G, and B values. And the intercept is sort of the circuit power, sort of the, think of it as the idle power. Even if the display is not emitting any lights, even the display is black, it still consumes power because you have peripheral circuitry that consume power. And so, yeah, so we're able to build a power model from color information. So then our goal is to, for each pixel with the color C, we want to find an alternative color C prime such that we minimize the power of the alternative color C prime, but guarantee that C and C prime are perceptually the same, which is to say that C prime must be inside the ellipsoid of C. Okay, now you can, with a simple arrangement, you'll see that this is a convex optimization, and there's actually an analytical solution. So so we can implement this as a fragment shader in the graphics pipeline in real time. It runs at a rate of 90 frames per second. So basically 0 performance overhead. So the geometric intuition here is that if you look at this, this is the ellipsoid or the ellipse boundary. So what I call this equal perception ellipse boundary. So all the colors inside the boundary have the same color perception. This line, so these lines are what I call equal power colors. Okay, so these colors on this line will have the same power. What we have to find is the sort of this line that is tangential to the ellipse, so this point represents a color that is perceptually the same as the reference color, but minimizes the power consumption. So the geometric intuition in 3D is that for every reference color here, right, we're finding a different color. So you'll see that all these colors, the reference colors, are moving toward a different direction to an alternative color. The alternative color is within the ellipsoid of the original color, but minimizes the power consumption. So if you put this into sort of the end-to-end rendering pipeline, what you'll see is that a GPU is doing the rendering here, and typically the GPU is going to generate a frame and then gets transmitted to the display, which then emit lights to users, to you. What we do is we, as I showed you, built a color perception model that tells us for each reference color at a particular eccentricity what are the perceptually equivalent colors. And we also have built a display power model that tells us how much power each color consumes. Now, given these two, and then solving the convex optimization problem, we can then generate a new frame. For every frame, we can generate a correspondingly new frame that gets shipped to the display that guarantees the same user experience, but reduce the power consumption. And so these are some results, I suppose. And so this is from one of the frames. What's on the left is a reference frame. And this is sort of a baseline where, and so this small circle represents 10-degree FOVA. So anything beyond 10 degree is what we would consider as peripheral vision because it's beyond 10 degree here. So this is a uniform baseline where you uniformly darken the pixel values outside the 10-degree FOVA. And this is the result generated by our rendering algorithm. And you'll see that the peripheral pixels are overwhelmingly green. If you notice the power model, blue pixels consume higher, much higher power as far as that particular display is concerned. And so our algorithm inherently removes or reduces the B channel. And so as a result, the frames images look overwhelmingly green. So you might think that I can still tell the difference by looking at this image. Well, the reason is because currently when you look at this from a computer screen, the entire image falls within your fovea. But when you actually display this on the VR headset, when user actually watches the video, all these pixels are actually in the peripheral vision. So that's why you could still tell there is an overwhelmingly green tint here, but actual VR users won't be able to tell. And so these are just some high-level results. There are 3 bars. The first bar is the original video without any optimization. The second is the uniform baseline showed you, and the third is our system. And this is the power consumption. And this is sort of the percentage of participants that could actually detect artifacts, meaning they are able to tell that some optimization is going on, their user experience is sort of affected. And compared to the uniform baseline, much fewer users are able to tell the artifacts here. So it's not 0 because every user is different, and the set of participants we recruited for building the model is different from the set of participants we recruited for evaluation. So I would be lying if the green bars here are 0, but the reason that they're not 0 is because every user is different. This also shows that we might be able to calibrate our model for each user, right? But so the point is that we can save about, I think, 21% power without necessarily affecting the user experience much. All right, so that sort of concludes the second part of the talk, and I won't really have time to talk about the third component, but I'll just go over this at the very high level, maybe using one slide. And this is sort of looking at what I call privacy preserving optical computing. And the idea is to capture no human recognizable images without sacrificing computer vision task accuracy. So, like, if you think about robots and self-driving cars and even AR, VR devices, right? So when they are wandering around, they need to capture photos, they need to capture images of the environment to understand the environment. Well, that also means that it's capturing images of you if you happen to be in the environment. Well, that leaks the privacy information about you. So I certainly wouldn't be happy about that, right? So wouldn't it be nice if we can have a camera that never captures images that are human recognizable, right? So if I show you a photo that's captured by my camera, you'll never be able to make out the details there. Like the 3 images here. So these are the 3 images, captured by the camera. And so if you look at this, you won't really be able to tell what's going on in those images. But these images encode essential information that allow downstream computer vision algorithms to still work, right? So if you run image classification, you'll know that the 3 images are, the first image is a rhino, the second image is a polar bear, and the third is a squirrel, right? So this is what our system is able to do. And so this is the optical setup, the setup of the optical system that we have built. And you can imagine what we're currently working on, which is to sort of reduce the form factor so that it can be packed into a mobile device. And that, we think that it's very much viable. And so that's what we're working on. Okay, so I'll just conclude, I guess. Hopefully I've convinced you, or at least showed you the horizontal pipeline, the horizontal paradigm, where you take a step back and look at the end-to-end application of these visual computing systems. Really, they are lights in, lights out. And it's a very interesting sort of system for us to optimize in the sense that we have to co-design across what I call information processing computing architectures. So typically these processors are what we call computer architectures. But if you look at sensors, optics, and displays, they are information, they process information, except optics process optical information, sensors process analog information, right? So these are all information processing computing architectures. And what I'm essentially advocating is co-designing across these information processing computing architectures. And this is necessarily sort of a horizontal thing. It's not to say that the vertical approach is no longer important. It's still incredibly important. It's here to stay, but we have to augment that, complement that by the horizontal approach. And I think one of the interesting and critical issues that we're currently looking at is how do you have sort of a CAD tool for this horizontal paradigm, the end-to-end system that can automatically generate such a system, right? Not only for the processors. And I think that would be sort of one of the grand challenges in this new era. Yeah, so with that, I'd like to conclude. So obviously all the work is done by my students, and I'm here to just talk about it. But obviously without them, none of the work is possible. And I'd like to also thank you for paying the attention and be happy to take any questions.
Thank you, Yuhao. Very, very interesting work. Yeah. Actually, I have several questions, but I would first to leave the opportunity for the audience. So, any questions from our audience?
Yes, I have a question. Professor Yuhao, so
Hi.
for few first line, you show a very tiny model that deploy on the image sensor, and you compare that with the UNet. So how can you reduce the model parameters or the model size to fit on that image sensor? Do you perform any architecture search, or you come up with a new architecture by hand design?
Okay, all right, good question. I think there are 2 points I'd like to make here around this slide. All right, so I have to say that this network which we run inside the sensor is not the gaze tracking network. You still have to run a gaze tracking network. This network, which runs inside the sensor, is just to extract or predict the ROI information. It just extracts the region of interest. And so this network is hand designed. It's just 5 layers. It's just very, very small. The reason it's small is not because we ran some sort of NAS. The reason it's small is because it's not actually detecting the gaze. It just extracts the ROI. And the ROI gets shipped to the processor on which you run the actual gaze tracking neural net.
Okay, thank you.
Yeah.
Other questions from the audience? You can unmute yourself or input a question in the chat box.
Yes, I have a question.
Hi.
Can I have a question?
Yeah, absolutely.
Okay, I'm not in your field. Actually, I'm completely layman. I'm from City College. I know Professor Yuan, so that's why I attended this seminar. And sort of wonderful, give me some idea about computer, and from last lecture, computer architecture, something. This kind of thing inside the chip, what's going on, we have no idea. Anyway, I have one little question. Your last one say you want to generate something, you don't want human being, any human being imaging can never be recognized. That kind of algorithm, whatever you say, that kind of technology. And I was wondering, this is not a good thing because this really give a criminal some sort of tool. They can hide themselves and doing the things, better thing. And camera, the main function, we want to have the camera be reflect the reality. And that's all the purpose, the ending purpose. We want a camera recording the reality, what happened. So I don't want to, I mean, from my common custom point of view, I don't want to see that kind of technology can hide somebody, human face recognition, nothing, and they can do all kinds of stuff. This is not good. That's my view. Thank you.
Yeah, all right. I mean, thanks for the question. I mean, I agree. I mean, I think is this what we propose is probably not going to be a universal solution. For instance, if you have dedicated surveillance cameras that are there to catch bad people, well, then you probably don't want to use this. But if you have a robot that's just wandering around, but then a robot is not supposed to be catch bad people as well, unless the robot is designed to catch bad people. But like if you just have a robot that's just wandering around in the departmental building, unless, as I said, unless it's a surveillance robot. But if it's just a typical robot that's assisting humans, the camera on that particular robot is probably not supposed to be capturing private information about other people. So I guess my answer would be that what we propose is perhaps not going to be a universal solution like what you suggested. And so on surveillance cameras, cameras are designed to capture, personal information, then what we propose is not going to be applicable.
Yeah, but then now this camera in your cell phone, everybody has that. So when you do something, the cell phone actually can take a picture. Is that right? And that's the thing. That's the thing. And we want to have, if you sell this kind of technology put on a cell phone, I'm not sure what will lead to finally.
Well, so what we're proposing is simply a camera, and so you can, a smartphone can decide whether to use a camera or not. So if you have a surveillance camera, if you have a surveillance system, you can choose not to use our camera.
Anyway, I just raised a question for discussion for later consideration.
Yeah, but I think it's an interesting one. Thanks for that.
Other questions? So actually, I have several questions, and the first one. So in your first part of your talk, you mentioned about like the in-sensor computing, and you said that so those the companies like Samsung and Sony, they actually already have some chip, right, to integrate such the. I remember you have one slide that already have the ISSCC paper.
Yeah, that's right. So let me go there. There are, a ton of papers on ICC lately on computational sensors. But there are, where is it? I'll show you that. Sorry, not here. But so the question is,
Yeah, here. So here when for this kind of the in-sensor computing paradigm, so we have kind of DRAM, right, in the sensor, right? Yeah, and so the computing is in the sensor, but not in the DRAM, right?
Yeah, so this is not analog computing. It's not in-memory computing. This is literally CMOS logic here, and the DRAM is literally just conventional low-power DRAM, I suppose. It's not analog computing. It's not in-memory computing.
And I was wondering, so why here we must use the DRAM because of the amount of the input data is quite huge. So
it doesn't. Well, I mean, yeah, it doesn't have to be DRAM. So if you look at Meta had an ICC paper this year where they had some basically SRAMs. It doesn't have to be DRAM. In this particular sensor, this sensor was used for one of the Samsung Galaxy phones, and they wanted to use it for slow motion capture. So like, 120 frames per second. If you want to capture 120 frames per second, the bottleneck really is how quickly can you transmit the frames outside the sensor. So it's bottlenecked by the data transmission. And so what they did is to have, I think, 1 gigabit of DRAM inside the sensor that buffers the huge amount of frames while the camera is capturing the scene. And once you finish capturing, the frames are then transmit outside the sensor.
okay, I see.
So
Thank you.
so this particular thing is dedicated for slow motion capture, but they also have some computation logic here.
Okay.
Yeah, it
Thank you.
certainly does not have to be DRAM. So Meta's recent ICC paper, I think, used an SRAM. So
okay, and also for your entire horizontal paradigm. So you mentioned that we can kind of blur the boundary across the different abstractions, right? And I was wondering, so is there any kind of a trend that, because that happens in the communication hardware a lot, that so we have kind of more kind of digital added analog parts there. And I was wondering, so whether this will also kind of happen like in the visual computing. For example, like whether we know that right now the very hot, like the neural rendering, right, network, and whether I did not work on that area, but I was wondering, I was curious, for example, whether you can further utilize that type of the technology to help you to further, like to reduce the computing burden onto for the input of the display and so on.
Yeah, I mean, neural rendering is, I think, incredibly interesting in, things like NeRF. I mean, achieves, much higher fidelity. I mean, because it's able to, I mean, as far as NeRF is concerned, right? So it's basically making up the light field that you normally would have to have high sampling rate. We are actually, I mean, so there are lots of neural rendering papers, and I think not all of them are reducing the load. I mean, most of them are, I mean, they are originally designed to achieve higher photorealism. There are certainly neural rendering work that we have been looking at that does reduce the computation load. So for instance, there is a SIGGRAPH paper from Meta that is, I think, called Deep Foveat, which essentially says it actually is related to foveated rendering, to the fact that your peripheral vision is has low acuity. What they did is you only render for the entire frame. For the foveated pixels, you render those foveated pixels with high fidelity, and for those peripheral pixels, you only sparsely sample them. You only render just just a few pixels in this peripheral vision, and then you use a neural net to then reconstruct the original scene. That kind of approach is, I think, is interesting. I think there are lots of neural rendering work that can be applied and integrated with foveated rendering, with the fact that your peripheral vision has low acuity. Deep foveat being one of them.
Okay.
And actually, there are foveated. Sorry, I was going to say that actually there are foveated image sensors, where the sensor, the pixel layout is non-uniform, so you can have denser pixels in the middle of the pixel array, and sparser, maybe even larger pixels in the peripheral. So you can even specialize and customize image sensors to exploit this foveation. And I think, yeah, so those are also incredibly interesting as well.
Okay. And another thing that maybe because you don't have enough time to present all of it. So because I think for the visual computing, another very interesting, in addition to the color, that is about the depth, right? The spatial information there. Right?
Yeah, so that right. So that's actually very interesting. We're looking at that. I think depth, there are many depth cues. So you have stereo depth queue and many other depth queues, and exactly what kind of depth queues are most important to depth perception, and how we can approximate them is certainly interesting. We're looking at that, so it's interesting you mentioned that, because yeah, that's exactly what we're looking at.
So maybe there's also some kind of the optimization opportunity there to explore the potential, like the redundancy there, to reduce the overall system power.
Yeah, so that's right. So that's basically one of the things we're looking at. Color is certainly one aspect, but depth. So depth is actually yeah. So it's much more complicated than color. Color is spatial. Depth. There are lots of depth cues. So it could be from stereo vision, or it could be from motion parallax, which is temporal, or it could be from your sort of experience, right? So, or it could be from object sizes. Larger objects are typically closer. Like, there are many depth cues that contribute to our depth perception. We need to find one that contributes a lot to the depth perception and a lot to the computation load to the power that we can save. And we're in the middle of figuring out what exactly which depth queue to focus on.
Okay. Thank you very much.
Yeah.
And is there any other question from our audience? Okay, so if no more other questions, let's thank our speaker again, Yuhao. So you give us very interesting, very inspiring talk. Thank you so much.
All right, yeah, thanks for inviting me, and thank you.
So our next seminar talk will be done 2 weeks later, because next week I will be on a trip. So our next talk will be on the October 20th, Thursday, still 11 a.m. Eastern time. And thank you everyone to join out today's talk. See you 2 weeks later.
Bye, everybody.
Bye, Yuhao.